Okay, thanks for coming back. And yeah, so I hope everyone now have enough energy to survive through the end of the morning. So okay, so the first lecture we discussed some examples and how these. Before introducing the technical tools, we discussed how actually they can be applied in concrete geometric situations. And I hope to convince you that these are. I mean, there are many places, examples where these things can be applied. So now this lecture, by the way, if you cannot read this clearly, please stop me. I try to write as clear as possible. So so this lecture will be about the decomposition theorem, for some general things about decomposition theorem. So for many of you, certainly this will bore you, I believe. But in any case, these are the basic notions that I will use again and again. So let me just spend some time covering it. So the main question I want to address is that, now, okay, given a proper or even projective map from x to y, so for convenience, let's assume for the moment that x is smooth, but this is not that important. So if x is not smooth, then we replace the constant sheaf by intersection cohomology complex, as I will introduce in a minute. So, but just for convenience, let's assume for this moment that the x is smooth. And what we consider is the general structure of. So okay, so we want to understand the cohomology of x. So okay, so we can do cohomology sheaf theoretically. So we push forward. Of course, everything will be derived. So we push forward the constant sheaf on x, and we just push forward to y. And the first part of this lecture concerns what we can say about it generally. And it turned out that even, so the decomposition theorem of Berlin and Deligne-Gaber as existence results. So it tells you that this guy can be split into certain building blocks in certain category. And even this existence result, so the existence of such a decomposition itself is a very powerful tool. It already tells us a lot of information concerning the topology of algebraic maps. Okay, so this, as I said, the main difficulty is that topology of this morphism is complicated because this object, you can think of this as a computation of fiber-wise cohomology because this is a complex in the base, and if you do base change over restricting over any closed point on y, this is calculating the cohomology of that fiber, and of course when the fibers are getting more complicated, this object is getting more complicated. So let me, but to get some idea of how general this structure looks like, let's start with smooth map as a toy example. So large part of this lecture would be about, yeah.
Can I just interrupt maybe something basic, but how does the pullback of that compare to the direct image of how does it behave under the pullback?
How, you mean?
High direct images when you pull it back, is it the same as the high direct image of the pullback?
I mean, so say that, so if this is a constructible object and if you restrict to y, so this is a graded vector space, and this is just as a graded vector space, this is the cohomology of x.
But if you have base change, you have a comparison of the higher direct images of the pullback morphism.
Yeah.
And the pullback of the higher direct image, is that nice?
Yeah, there's some general axioms, the base change theorem, and you probably have to switch the star by shriek, and yeah, there is a base change theorem, yeah. And over a point, this is what I'm talking about.
Sorry, could you say what is the subscript of the bracket and what is the subscript of x in the second homology? Because it's not so, it's too small from here.
You mean this line?
Yeah.
So
RF, Q, and then
RF lower star, just X, sorry. This is the constant sheaf, and y is a point on the base. You have a push-forward complex that restricts to a closed point on the base.
It's a point.
It's a point, yeah. So y. Yes.
And then h star of x subscript what?
Y, the same y.
Okay.
Okay, I mean, this is just a sign of mark. I'll erase it. Okay, so let's assume that f x to y. Consider the general situation where there's no singular fiber. So this is a smooth projective map with both x and y smooth. So it's really smooth vibration. Yeah, so the case without singular fibers, which is the most complicated case we will discuss later. So the theorem of, is this visible? Are people there? Yeah, that's.
There is a shadow.
I understand. So that's why I'm asking. So what I can do? Like this?
Yes.
Okay. Yeah. Yeah. Please stop me if you feel it's no longer visible. I always forgot how hard I should push. The theorem. Okay, so the theorem by Junliang is that, okay, we first state what the decomposition theorem looks like in that situation. So the notation, I use R to denote the dimension, the complex dimension of the fiber. You use R to denote the dimension of the fiber. So then there are two parts helping us to understand what's the push forward of the constant sheaf. The first one is the more traditionally called a decomposition theorem. So in other words, I would like to view the decomposition theorem as a package of two things. One is really the decomposition, which tells you that the push forward of the constant sheaf will be split into local systems calculating fiber-wise cohomology. So this is an object which is a complicated object at the base, and then it splits into like every RIF lower star. This is calculating the fiber-wise HI, which is a local system because this is a smooth vibration, and then you shifted it correctly at the correct place. So this I goes from zero's cohomology. So since R is the relative dimension, so I goes from 0 to 2R. So this is an identity which happens in the bounded derived category of constructible sheaves on Y. So in other words, the decomposition theorem in the smooth case tells you is that you can pretend as if you're pushing forward to a point. So if you push forward to a point, what do? You consider the cohomology of that fiber. And the right-hand side, that just tells you that you can calculate the cohomology degree by degree. The every HI. And but this holds in family, which itself is a very strong statement. Okay, so here the remark is that, so keep in mind that the Ri F lower star Q, so this is a local system. Computing HI, the ith cohomology of the fibers. Okay, so this is the first statement, which splits the push-forward complex, and the second part is the semi-simpleness. Semi-simplicity. So this says that each local system on the right-hand side can further be decomposed into really the building blocks. So each Ri lower star Qx. So this is the local system, but it's actually this is semi-simple. More precisely, this says that it can be decomposed into L alpha, which every L alpha is a local system, which of course is a sheaf on Y, and with L alpha, a reducible local system. So for a local system, it's a representation of the fundamental group of Y, and being irreducible means that the representation is reducible. So this is the corresponding pi 1 Y wrap is irreducible. Okay, so these two are the general statements concerning the decomposition theorem of the smooth case. And actually, to some extent, so in the general case, they are also true. So we have two statements. One is the decomposition into objects in each cohomological degree, which in the case of singular fiber, when the singular fiber showed up, it would be certainly more complicated than just taking the relative cohomology, but it will be taking the perverse cohomology. And the second statement says that each object in the heart, in the abelian category, can further be decomposed into simpler objects, which are building blocks. So remarks. So how to think about theorem A, the part A, the decomposition part? So the part A actually, you can view this as a sheaf version or sheafification of the degeneration of the Larrey spectral sequence. So why? Because we pick any open subset of Y, say U. Then if you evaluate both sides on that U, then what do you obtain? So I just take the Y as the entire open subset, and so then so the left hand side is just calculating the cohomology of the total space X, and the right hand side, well, it tells you that you can calculate the cohomology of the total space in terms of the cohomology Ri f lower star Q X. So this is, you see, by the appearance, it looks like this is the E2 degeneration of the Larrey spectral sequence. And the thing I want to emphasize is that this is really a statement about the algebraic geometry. Because, so maybe let me just write this down. This is the E2 degeneration of the Larrey spectral sequence. Okay, but this kind of phenomenon actually is very algebraic. So if you, a typical example where everything fails is the Hopf fibration. So if you, this is a very famous fibration of S3 over S2, whose fibers are S1, then it's so obvious that, I mean, you don't have this. So theorem A fails for the Hopf fibration. Otherwise, if the cohomology can be obtained by push forward the relative cohomology and then calculate the local system on the base, but you know that S2 is simply connected. It's just a two-dimensional sphere. So any local system is trivial. So if the decomposition theorem holds, this will tell you that the cohomology of S3 can be written as the tensor of the cohomology of S1 with the cohomology of S2, which is certainly wrong. Okay, so in particular, this example shows that if you have a smooth map between manifolds, then certainly this kind of thing is wrong. And this contradiction. Actually, the Ling's proof of both A and B are through Hodge theory. So let's explain, before moving on, let me give you some feeling about why such thing is true, or how the decomposition theorem holds by proving the cohomological version of A. So I would like to explain how the algebraicity of the morphism can be used to split everything. So we prove A cohomologically. So the idea is, of course, to use Hodge theory. So just to comment that, so the smooth case, this was first proved by Ling using Hodge theory, and when there are singular fibers, then Ling's original proof is to pass to characteristic P and use the Frobenius, the weight theory he developed to prove the weight conjectures. And then the second proof was given by Saito, again developing a weight theory purely in the characteristic zero world using Hodge modules. And later, the Decatado Migolini realized that actually, even if there are singular fibers, then the corresponding statements A and B actually can be obtained from the classical Hodge theory. So let's prove the degenerates of the Lorentz spectral sequence using Hodge theory. So let me just first write down the Lorentz spectral sequence. So E2 page. So yeah, I mean, when I was a student, the most painful experience is to write down a spectral sequence, and I hope I can write down the index correctly. So this is H, P, Y, R, Q, F star. So this is the Lorentz spectral sequence. X. Okay, so the differential of the is dr is from ER so here are so this is R P plus R, the arrow is going in this direction, so P plus R, and the Q minus R plus 1. So it starts with, so for R is equal to 2, so this is just E2 PQ going to E2 and P plus 2 and the Q minus 1. And then, if the differential is 0 for the second page, then you take the associated grade and you get a third page and so on, you continue. Okay, so what we want is that the E2 degenerates. So in other words, we want that dr is equal to 0 for any r at least 2. Yes, you have these differentials and you want to show that they are all 0. Okay, so I just write down the index, how they look like. So dr looks like, okay, so h p y r q f lower q, and this goes to h p plus 2 y and r q minus r plus 1 f star q. Okay, I'm just writing down the spectral sequence. Oh, yeah. Okay, maybe. Let's start with 2. Thanks. Yeah, I only proved this for 2, but for general R, it's the same argument, as you will see. Okay, as I said, the degeneration of this one certainly has something to do with that the morphism is as algebraic. Okay, so let's take a relative ample class on X. So in particular, this eta gives you a class in, so fiber-wise is an H2, so this lies in actually, it naturally induce a class on Y and R2F star QX. Okay, so you know that from Hodge theory, you know this copying with this induces a Laffier symmetry. So by Harder-Laffier, you can decompose the push-forward complex using this eta, the nilpotent operator, into primitive classes. So this, of course, for a single cohomology group, that's just the classical statement we learned in Hodge theory, and this works relatively. So you have RQF lower star PX. We can first use the Harder-Laffier and this eta to decompose it into primitive classes. Yeah, sorry, I'm just prim. So you have the primitive classes, and also, of course, you have the more, which is given by the image of eta, and these are the primitive classes in degree q minus 2, prim, f lower qx, and plus eta square, and so on. So you just decompose the cohomology into the primitive parts, and then I'm claiming the proof is done. Because you see, okay, so we want to prove something like that. So since every time, so it's an easy observation that every time we only need to treat the primitive class, because otherwise you go back. If a class is given by the image of eta, then we go back. So since we know that the spectral sequence, this differential is compatible with taking cut product with eta. So every time we only need to treat the primitive classes. Otherwise, we go to a different degree and treat the classes there. So this is a direct exercise. We take RQ prim, F lower Q. And OK, so the dr, maybe I'm just writing d2. Is this goes to p plus 2 y and r q minus 1. OK, so this is the differential. So I want to show that this is 0. Every class is sent to 0 here. But the thing we know is that we have a hard lefts. So the idea is that we take the cup product for a power of this so that the right-hand side is just an isomorphism given by hard lefts. And then because by degree consideration, the left-hand side will go beyond the hard lefts range, so it will be 0. And so let me just write this down. So this is copying with eta r minus q plus 1. So if you copying with r minus q, this is an isomorphism, but you do one more, so it's actually, this is a 0 map. So this is p, y, r, 2r minus, OK, q minus 2, and f lower star qx. Sorry for the complexity of the indices, but so this is the differential. And the one here is p plus 2 y. Yeah, sorry for that. 2r minus q minus 1 and rf lower star qx. OK, this is the same, r minus q plus 1. OK, you just consider the compatibility between the array spectral sequence with the cup product with a relative ample class. And then, so you have two morphisms. So this already, having the relative hard lefts is already enough to force everything to split. Because then the left morphism is 0 due to the definition of primitive classes. And the right morphism is iso, which is the consequence of the hard lefts. So combining them, you obtain that the differential has to be 0, because this is, so on one side this is 0, on the other side this is an isomorphism. So the compatibility tells you that it has to be d2 is 0. And they run the same argument, for dr. And you notice that as long as r is at least 2, then this works. OK, so this is the proof of the part A, essentially the cohomological version of part A. But then you can push this argument to the sheaf theoretic level and prove this for the local systems. And the part B is a more complicated Hodge theoretic, general Hodge theoretic fact that any variation of polarized pure Hodge structure is semi-simple. The original argument uses the harmonic metric. I mean, this is a transcendental proof. But the general fact is that if you have a pure variation of Hodge structures, polarized Hodge structures, then the corresponding local system was always semi-simple. Okay, so here are some discussions about the decomposition theorem for smooth morphisms. The natural question is, what happens if there are singular fibers? Which is the more useful case? And the thing we want, of course, is to decompose the push-forward complex into building blocks as in A and B above. Okay, so assume we erase certain part of our memories, and we do not know. Assume we have never learned perverse sheaves and perverse T structure and these things. Maybe the first question we can ask ourselves is whether, we just copy exact statements of the theorems A and B in the Lin theorem before, even with singular fibers. Then whether this is still true, and the answer is no. And this answer, there is an obvious obstruction coming from Hodge theory. So general case. So let's assume x to y is a general projective. And the natural question is, do we still have okay, we can just write down the same statement, and everything, of course, makes sense. So you can just take the RQ F lower star QX bar and shift it by minus Q as you want. And then when there are singular fibers, these are sheaves. These are constructible sheaves, no longer a local system, but it still makes sense. So the answer, of course, is no. And that's the reason that the thing is so complicated and so interesting. And so there is obstruction. There is obvious obstruction from Hodge theory. Which let me explain a little. So there is no chance that such a thing is true, and actually the obstruction tells us that how to fix this problem to get a better object, which is our main character. Okay, so to see that this does not have a chance to hold, we take y to be a normal singular projective variety. We pick your favorite, you just write it down, random projective variety. It may be very singular, normalize it, you get your y. And then we just take F to be the resolution of singularities, resolve the singularities. So we know that if you have a decomposition theorem, then the Leray spectral sequence will degenerate. And actually, there is extra information. We know that the Leray spectral sequence is not only a spectral sequence of vector spaces, but actually a spectral sequence of Hodge structures. So all the morphism would be morphism between Hodge structures. So the Leray spectral sequence is compatible with Hodge structures. So if it degenerates, then you get the obvious obstruction by noticing that the singular cohomology of y will appear as a piece of the singular cohomology of x. But this sentence holds in the sense of Hodge structure, so this is impossible because if you find a random y, then the Hodge structure on the singular cohomology is not pure. So if it degenerates in E2 page, so we will have the cohomology of y, which is given by a cohomology of y, the R0 f lower star q, which is just the q of y. So this will be a piece of the total cohomology of x at the sub-Hodge structure. And this, since x is a resolution of singularity, so x is a smooth projective, so this is always a pure Hodge structure of weight k. And that this, in general, is mixed. So a mixed Hodge structure cannot be put inside a pure Hodge structure. So this is impossible. Since x, which is smooth projective, has pure Hodge structure, but in general, y can be mixed. Okay, so this is the bad news and also the exciting part, because then, so there will be a way to fix what's happening here. So the this issue is fixed by, of course, the Beilinson-Bernstein, Deling, and Garber, who tells us that, so okay, so you have this Q actually comes from this first summand of the push-forward complex of this birational map. And we should replace Qy, which is the constant sheaf on the singular variety, by a more complicated but nicer object. Which is the, so this will be the intersection cohomology complex. Usually people call this IC complex because it stands for intersection cohomology complex. So you want to make sure that even y is singular, then the complexity of the singularity of y will be encoded in this object, so that if you take the cohomology of y, not for qx, but if for this IC complex, which will be denoted as the intersection cohomology of y. This is the intersection cohomology, is still pure when for y singular. Okay, so Francisco, where should I stop?
20 minutes. Yeah.
20 minutes, great.
And is everything more visible for all of you? Yeah? Okay, they are not complaining.
Okay. Okay, in the following, I will first write down what's the solution to this. Of course, this will involve a lot of abstract things. If you have seen this before, you definitely will be bored. If you haven't seen this before, this won't be very helpful. So let me do this part quickly. And after that, I will focus more on how we think about it and so the construction. So yeah, if you have seen this before, then certainly you can take a nap. Okay, so again, as I said, because for completeness, I will write down this anyway. But I don't want to spend too much time on explaining this abstract notion. But after that, I will explain the thing I found helpful about how to think about it. So okay, so for y as before, as a variety which might be singular, and you have we consider the triangulated category of a bounded derived category of constructible sheaf where there is a dualizing functor given by taking home with respect to the dualizing complex. So the dualizing complex is you consider the morphism from y to a point, and you take the p upper shriek of the constant sheaf downstairs. But Poincare duality, this will be q of y shifted by 2 times the complex dimension. So if y is smooth, this will be omega y is just the constant sheaf of y shifted by 2, I think twice the complex dimension of y, if I'm correct. Anyway, some shift to make the Poincare duality correct. And when y is singular, then because the upper shriek is complicated, so this is a complicated object, and then this is a dualizing functor on this object. Okay, so then I'm writing down the T structure. So these are called perverse T structure. Given by so-called support property. So this half is given by the object on y, satisfying that if you take the, okay, so this is when I first saw this, I was very confused, so I hope it's no longer the case. So if you take the standard cohomology sheaf of this object, you take the negative I degree, then you consider its dimension, the dimension of its support. It's bounded by I above for any I. So this is called the support condition. And then the other half is defined very simply. So it consists of objects on Y satisfying that its dual satisfy this. Okay. It's not very helpful, right? If I just write this way. Okay, so this is called perverse T structure, and then you can check this satisfy all the axioms of a T structure, so that I can consider the heart, which is the full subcategory lying in the intersection of both. So meaning that these are complexes such that it satisfies the support property, and that the dual also satisfies the support properties. And So this perf Y will be the category of perverse sheaves. So you can, if it's your first time to see, it's the first time to see this definition, you can try your favorite object, favorite sheaf, and test with these conditions, and you see whether they are satisfied. But if you don't get a good feeling, if you feel that you don't get a good feeling about it, don't worry. I will write down certain objects in this category, which will be helpful for us to visualize how it looks like. So let me first give you some examples. We consider C2, and let's write the x-axis to be x, and then write a point here. Then you can check immediately. Then if you consider a constant sheaf, well, first, this is not a perverse sheaf. You have to shift it correctly. You shift it by 2. So making this concentrated, so this will be concentrated in degree minus 2. Why? Because of the support condition. You take I to be you take I to be 2. So then the H minus 2 is it's just this constant sheaf, and the support has dimension 2 because it's everywhere. Okay, but what if you want to make what do you want to make some perverse sheaf supported on X or P? You have to make a different shift. So and then if you make, for example, the constant sheaf on X, you have to change the support. You have to change the shift, because this is a perverse sheaf. But if you do this on X, you only are allowed to shift it by 1. So this will be concentrating degree minus 1, and the Q P. This is a skyscraper sheaf, and you don't do any shift. So these are all perverse sheaves. On C2. Okay. So if you are bored, here are some fun exercises for you. One of the interesting way of constructing perverse sheaf is you start with some open subset. Say we consider Q, and you remove the point. You consider C2, you remove the point, and you consider constant sheaf. Okay, so if you shift it by 2, this will be a perverse sheaf on the complement of a point. So try to verify. But then you just do J lower star, Rj lower star by extending it. And so the question is whether this is a perverse sheaf. So if you verify the answer here, you can also replace P by X and ask yourself the same question again. Okay, so now let's come back to constructing the intermediate extension. And this is the object which will underlie the main theory of support theorem. So I have roughly 10 minutes. Okay, so the purpose is we want to construct more interesting perverse sheaves. And so the process is that we can always start with something easy, which is like this. So we start with some open subset, which is smooth, which is basically a manifold, a complex manifold, and we can just take local systems there with appropriate shift. And these are always perverse sheaves, and then, okay, then you can just use 6 operations to extend them. And so the upshot is that if you do this correctly, then they will give you essentially everything. Let me introduce the intermediate extension. So you start with an open embedding with use some smooth open subset of y, and then there exists a functor called intermediate extension. So it will be denoted by JP, which stands for perverse and lower shriek, lower star. It's a weird notation. I'll explain it. Which goes from perverse sheaves on U to perverse sheaves on Y. And then, okay, so if time permits, I will write down this functor at the end. But so this is purely a functor built up from the 6 operations. You use the perverse truncation functor and the lower star, lower shriek. You can just build this functor. It's very concrete. And the upshot is that if you start with a local system on U, and you shift it correctly, so I mean, you know that the local system on U is not a perverse sheaf, but you can shift it correctly by the dimension of U. This will satisfy the support property. So this will give you a perverse sheaf on U. And then the intermediate extension on Y associated with this local system is you just apply this functor. This functor is called the intermediate extension. Intermediate extension functor applied to this local system with appropriate shift. That's it. And well, this will be landed here. Perv of Y. Okay, in other words, the intermediate extension allows us to construct interesting objects from the very, very simple objects. So we assume we have a singular variety. We threw out all the things we don't like, the singular locus. Only by looking at the smooth locus, we can construct a bunch of interesting, like nice perverse sheaves, which are shifted local systems. Then we do intermediate extensions. So in other words, all the complexity are lying in this functor. Okay, so but it's by an abstract description of the functor. So fact. We know that the intermediate extension is compatible with duality functor. You take the dualizing functor of the object, and this is the same as you first do the intermediate extension, and then you apply the dualizing functor. So this is dualizing functor on U, and this is dualizing functor on Y. Okay, so in particular, let me define the IC of Y, which is the intermediate extension of the trivial local system. So you pick any U, smooth. You pick any U which is smooth open, and you shift it correctly, and you apply this intermediate extension. This will give you the object on on the global Y, and this is self-dual because of this. So because this is self-dual on U, and the intermediate extension exchanges with the duality, so this is self-dual. I.e., if you apply the dualizing functor to the intermediate extension, it will be IC of Y. So, and this is actually one of the original motivations for introducing by Gorin schema Fersen to introduce the IC complex, which is to fix the Poincare duality. So in particular, this implies that if you take global cohomology of IC, which is the intersection cohomology, this satisfies the Poincare duality. No, the IC, so intermediate extension in by definition is to go from the perverse sheaf to perverse sheaves.
So there's a shift by del U already in the definition of IC1.
Oh, yeah. Yeah, you know what I mean. Yes. Thanks. Yes, thank you. This is better? Okay, lastly, just let me conclude with a more general construction, which in fact gives us everything. So a more general construction. So far, what we have done, okay, we want to construct interesting perverse sheaves on some singular variety or complicated variety. So the way we do is that we consider some open subset of it, and consider local system there, and then we apply some functor, which gives something global. And this almost gives us everything we are interested in, except that, so we can take a step back. Instead of starting with some open subset, we can start with something locally closed. So yeah, let me finish by writing this. So you have, you can consider U, which is the closed open subset of Z. And you just replace Y by, you can replace the original Y by any closed subset. So then it's the embedding of U inside your original Y will be a two-step embedding, which is open immersion, closed embedding. J and I. So this is open and closed. Okay, so then I can start with a local system here to build up something on Y by, so that's called IC on Z and L. This will be denoted by, you first do the intermediate extension for this Z, extending the local system with appropriate shift. Now this will be a perverse sheaf on Z. And then you extension by 0 by just considering I lower star. And this will give you a perverse sheaf on Y. So this is a perverse sheaf on Y. Okay, so these are, so as I said, so these are all the objects we care about and all the objects that will show up in the decomposition theorem. So in other words, the objects we care about are built up from two things. One is Z, which is a closed subset in the variety we care about, and this Z will be called a support. And then the other thing is L, which is a local system, not necessarily on this entire Z, but only can survive. It can survive only on an open subset of the support Z. And so in the next time I will write down the decomposition theorem, which says that everything which showed in the decomposition theorem are of this form. And so in other words, if you want to decide the decomposition theorem for the morphism, it suffices to decide what are the supports C that showed up and what are the local systems. But in general, this is a very difficult task, and I will explain in certain situations this is very doable, and there will be interesting consequences. Okay, so